The key data structure that handles all of these things for C is a stack. And we're going to draw a stack upside down from what you might usually draw it. So we call this bit that's on the top of the slide, we call that the bottom of the stack. And the part that's at the bottom we call the stack top. And we call this the top and that one the bottom because when we add things to the stack, we're going to add them here. But we draw it upside down because the way addresses work in memory, the higher addresses are up here. So if you have a lower address, that means something more recent on the stack, something hotter on the stack, or shallower on the stack. If you have a larger address, that's deeper in the stack. Every time we push something, the stack will grow this way towards lower addresses. Every time we pop something, it'll grow towards higher addresses. Right, so there we've popped three things. The stack top is moving towards the stack bottom, so the stack bottom stays put and the top grows. And then the top is going back down in number as the stack grows. RSP is here because we're always going to keep the top of the stack in that register, and that's why it's called RSP. It's a stack pointer. Just to make that concrete, suppose that our stack bottom is at hex 8 with 6 zeros after it. If you throw a few more zeros at the end, that would be realistic, but this is close enough for our purposes. So you can see that as we go towards the top of the stack, the addresses in memory are getting smaller. You can also see that I've drawn 8 bytes here for each segment of the stack. So there's an 8-byte value of 2 that's most recently pushed on the stack, and then this hex 789 ABC, and so on. I'm also showing some registers, REX and RBX, and RSP. So there's a little redundancy in this picture. This address matches up with this pointer, that address that it's pointing to on the stack. We talked a little bit before about the pop operation, and now we can show it more explicitly in terms of the stack. So popQRAX means take what used to be the most recent thing on the stack, remember that was a 2, and move it into the register RAX. And then at the same time, or after moving it, depending on how you want to think about it, pop it off the stack, that is, increase the value of RSP by 8. Right? Why 8? It was because we popped a quad word off of RAX, and again, each slot in this picture of the stack is 8 bytes. If we pop again, this time into RBX, then we'll take this value that's currently on the stack, hex 789 ABC, and put that into RBX. Again, RSP grew by 8 in terms of addresses. The stack got smaller by 8 bytes. We could push the value RAX back on, so that would be push Q RAX, and now that 2 replaced what used to be past the stack top. And it's 2 because that was the value of RAX. So we did 2 pops and a push that effectively moved the 2 1 space deeper in the stack, but it's still at the end here the most recent thing on the stack. Pop Q and push Q are really shorthands for a couple of move operations. And it's sometimes, or arithmetic operations. So here I have, instead of using push, just use sub Q8 RSP. So what that means is that RSP is decremented by 8, which means the stack got bigger by 8 bytes. We don't know what's in that stack region. Because this particular slot spent some time on the stack but lower than RSP, beyond the stack top, the operating system might have caused that to change for various reasons. So when we just use sub Q like this to move RSP, there's no particular value here. This is still a useful thing to do because it makes room and we can start storing things on the stack, as we'll see. And correspondingly, we might move the stack pointer back, do something like a pop, but this time with an add, again changing 8 bytes. The value of RSP, that's the same as a pop, it just didn't put those unknown values into any particular register. I'm emphasizing that all of these are 8-byte operations in this picture because it doesn't have to be. Here I'm drawing the picture again, this time just using 1 byte as each stack slot. And like the rest of memory, the stack is byte addressable in this way, and although we don't usually do it, we could imagine changing the stack pointer at the byte level. So we might pop a long word that is just 4 bytes. If we look at this byte picture, that means RSP changed by 4 bytes, and we have a little Indian view here, so FD was the low byte, FF was the next byte, and so on, going into register RAX, or the low 32 bits of that. And A program can use the stack at both byte and word and long word and quad word granularities if it wants. Right? In this case, I'm pushing 2 bytes back on from register RBX, just the low 2 bytes there. So hex 41 ends up being the hottest thing on the stack at this point.